Okay, so here we are. We today are going to start talking about stress and strain for bending. I love this lecture, even though there's a huge chunk of it that you don't need to memorize. I have to show it to you, but it's really kind of fun to see all of these things come together. So we will be doing a few examples at the end, and there is a zone in the middle of this lecture where it is to talk you through the process so that you can say you have learned this process. I'll try to be very explicit on what you need to know and what you don't need to know, but you should listen to all of it, because when I say you don't need to know it, it means that I'm not going to test you on it, but I do need to know that you've listened to it. So today's lecture, I might not get through it all at once. I normally like to do it all at least in a tight block, even if I'm starting and stopping to do calculations. I like to do it in one chunk of time, but I am running low on time today. Like I had said, Duncan had a crazy high fever yesterday, so I lost basically 24 hours. He seems to be okay now. I was able to put him back with the nanny, but he still has a bit of a fever, so we're watching him closely. We don't think there's no way it's COVID, because we live in a very tiny little bubble and see nobody. So I can't imagine it's that. It's just normal kid stuff. But when your kid's sick, it's hard to think about anything else. So let's start by recapping what we talked about last week. We're going to kind of recap the principles of stress and strain. I'm also going to recap what a neutral axis and a centroid is, and this is building up to be able to do a calculation that is very important that you see. I'm going to recap equivalent forces and couples with a quick example. I'm going to recap internal forces, and I'm going to recap internal stresses and how you draw them and where you draw them, and loop that in with centroids. And that's all over a refresher, just to prepare us to talk about beam theory, or Bernoulli's hypothesis of beam theory. So we're going to recap all of that. This is all stuff that we've talked about before, but it's just a refresher because it was scattered throughout about 7 different lectures. So we're going to bring it all out, just a quick refresher, and then I'm going to talk about stress in a beam, and we are going to analyze elastic bending and plastic bending. We're going to learn how to derive the equations to be able to calculate that, and then once we see how that's done, we'll be able to see that there's some kind of quick shortcuts we can take. What we've done for a lot of things is that we've worked out the long way and then seen that there are some quick shortcuts. But I need to show you the long way because that explains where it comes from and how we came about being able to do it this way. So last week we talked about stress. And stress is force divided by area. And it is to the unit element what force is to the overall object. And we can define it with an overall object because we have a force and an area. Stress takes us back down to the unit element and allows us to talk about it as a unit element. Strain is to the unit element what deformation is to the object. And we classify it as delta L divided by original L, or the change in length divided by the length. Sometimes we'll write the O, sometimes we won't. In fact, I hate this slide. I thought I had gotten rid of this ages ago because I hate that length is after application. I'm going to fix slide 3. So this slide is going to look a little bit different to you, so make sure you take a look at that. It's going to match what you've done before. So I'll call length after LA, and L is the original length. It just makes it a little bit cleaner than this ridiculousness. And so that is a unitless measurement, and it is kind of a classification of deformation on a unit element. And then modulus of elasticity, or stress divided by strain, sometimes called the Young's modulus, is what we use to measure the stiffness of a material. What we care about is it on the...
Stiff drink?
Good one. Good one. I would love...
coffee?
No. No, thank you.
Water?
I have some. Thank you. Right. Modulus of elasticity, stress divided by strain, or MPa divided by a unitless element, leaves us with MPa. And it is how we talk about stiffness for materials related to each other. High E, you've got a stiff material. Low E, you've got an unstiff material. We talked about stress-strain curves last week, and what we really care about is this zone here, which is the slope where it's in the elastic zone, or if we unloaded it, it would go back to its original shape. Many materials, when they hit the end of this elastic zone, fail. That is it, that's the end of it, because they are brittle materials. Wood is a brittle material. Concrete on its own is a brittle material. Steel is not a brittle material, it is a ductile material. So when it gets to the end of this zone, it enters a plastic zone where there can be permanent deformation. Even if we release the load on the object, it won't go back to its original shape. And so steel is one of those materials. Concrete, if we put steel inside it, can be ductile, but the concrete itself is still brittle. So we like this zone right here, and for what we'll talk about, we'll just maybe, we'll push just past this a tiny little bit going forward in this lecture. We talked last week about how knowing that stress equals force divided by area, and knowing that strain equals delta L divided by L, and that modulus of elasticity E is stress divided by strain, we can put those together and rearrange it so that any one of those is the unknown in the equation. Or we can set that to be equal to something. And we can rewrite that in all of these ways, depending on what things we know and what thing we want to know. So that we can try to determine some of these. And last week, we only really talked about this axially. So this week, we're going to go a little bit further. But before we do that, let's remind ourselves of some things we've talked about in some past lectures. Mostly just so, you know, these things aren't that foreign. I used to not give this little intro, and people would get really thrown off when we do the derivation in a little bit. Even though it was all things they had already learned, it seemed a bit random to them to be pulling them from other spots. Okay, buddy. It seemed a bit random to people, so this was about just trying to bring it all together so that it's a refresher. Do you want to just, he can lay in my arms for a little bit while I talk. Do you want to just lay here and listen to me talk? Yeah. Okay. So the neutral axis is the axis about which an object will rotate if spinning freely, or the median line. The mean axes of mass, gravity, or inertia, if you will. So if you were spinning in space, or for anyone who watched Gravity, you know that there's a point that you might spin about. The centroid is that point in a body. It might not necessarily even be within the body. It can be outside of the body, depending on the shape and where the mass is. But it's the mean position of matter in a body. The center of mass, center of gravity, or center of inertia. The point at which a body will rotate if spinning freely. Or, if you want to say, it's the intersection of all the neutral axes or median lines. I'm talking to all my students, buddy. No. And you want to just sleep here? Or are you getting down? Can Daddy let you back in with Jackie?
Yeah.
Or can you do it yourself? He sat still. That tells you how sick he is. You guys remember equivalent couples. So, when a force is applied concentrically to a body, it will translate, or if you apply it through the centroid, it will translate in line with the applied force. If you apply a moment about its centroid, it will rotate like that. If we apply a force eccentrically from its centroid, if we apply it eccentrically from its centroid or not through the centroid, it will slide and rotate. Anyone who's ever gone skiing knows that this can happen. It is the same as if we applied a force directly through the centroid and a moment on it. Remember, a force through the centroid made it slide, and a moment made it spin. So if a force eccentric from the centroid made it slide and spin, the combination of a force through the centroid and a moment about the centroid should also make it slide and spin. So that means a force eccentric to the body, or from the centroid, can be the same thing as the force through the centroid and a moment about the centroid. So we can equate those two. And that distance from the centroid defines how much it spins, or what we call moment. Well, that's also annoying that I have that moment spinning in the wrong direction. Slide 13. Moment, wrong direction. Because, of course, if this force is over here, it's trying to spin in that direction, not that direction. So, if we had this cantilever that was fixed right here, or say we had this, and this is held rigid right here, and we applied a force on the end, and let's say this was 2 meters long, and I'm applying a 10 kilonewton force right here. The moment that we define right here is the force times the eccentricity. And so how are we defining what the centroid is? Well, this is where it's being held rigid. So our force times our distance is the same as 10 kilonewtons right here and 20 kilonewtons about that point. Remember, we at the end of last term spent a lot of time saying for this not to move up and down or slide in space, there has to be reactions here. What we were essentially doing is figuring out the equivalent force and moment that this causes, and then applying the reaction. So we last term calculated that there would have been a 10 kilonewton upward reaction and a 20 kilonewton meter moment reaction in that direction. So this is just showing us the force, not the reaction. But this 10 kilonewtons, 2 meters away from this point right here, is the same as 10 kilonewtons through that point with a 20 kilonewton meter moment about it. All right, let's talk about the unit element and equivalent force couples for a minute. So if this is our object with a centroid, and we have a force, some eccentricity away from it, this time I've drawn it in the right direction, this is the same as the force in line with the centroid and a moment about the centroid. And the moment is force times eccentricity. Okay, let's talk about stress and force and centroids, because we need to know how to make this make a little more sense to us if we're trying to break it down. Remember those analogous point loads that we talked about? We know that those were very handy because they let us do quick calculations. And we knew that they were only good for that one particular little micro section that we were drawing, but they were very handy when we needed them. So we need to be able to do that for the stresses that we're applying to things. So if we have this object with a stress on it, we know that it's the same thing as the force over this area. So if we had this object with a side A, B, and C with this stress on it, we know it's the same thing as P over the area A times B. We have an area, we have a force. The last one was an undefined blob, but this time we have a dimension. But it's a pain in the butt to draw things in 3D all the time. That's why we don't draw things in 3D all the time. Some of us can't draw things in 3D very well. Some of us do it very well. He's really, really good at it. Wait, I want to show them one just because. Were you using this? He'll do this on the train, and I can't. He can like just sketch things like this on a moving train. I couldn't spend 2 days and draw that drawing.
I'm curious, which one did you show them?
Oh, I just zipped through and found something. You gonna find a good one?
No.
You gonna find a favorite? And now he's just admiring his handiwork. So, since it's really hard to draw in 3D, we often simplify the world into a 2D diagram. So, we have A, and we have C, which was the height, but B disappeared. It's like a mirage, it's gone. But we know it's there, because, look at this says stress. And stress is over an area of some sort. So even though we're only seeing the dimension A and C, we are talking about it knowing that there is some undefined dimension B back there. And that's going to be handy because we're going to do some drawings and sections where we just have to remember that B exists. Sometimes you'll have that information about what it actually is, and sometimes you won't. So this is the same drawing as this, but only in 2D. So this is also the same drawing. We have the force P, and the force P so this stress was force divided by area, and we know still that that B is there somewhere. So let's look at varying our centroid. We have the centroid of our object, and we have the centroid of whatever this stress is, because stress does not have to be applied equally. I'm trying to think of a good example in the practical world where stress isn't applied evenly, but they might. Okay, he's leaning forward on his toes. You can't see that. But so if you stand perfectly with your weight over your feet, you know that your force is being spread out pretty evenly over your feet. If you lean back just a little bit, you can feel that most of your load is coming down in your heels, but your toes are still doing a little bit of work. So we have the centroid of the stress and the centroid of the object we're applying it to. What happens if we vary the centroid of the object? Well, now we have an eccentricity. So we have the centroid of the object, and we have the force that would have been applied over this area A times our unknown distance B. So we're remembering that B is still there, but we've got our eccentricity now. And then we've got M equals P times E. What happens if we vary the centroid of the stress? So last time we varied the centroid of the object. Here we're going to vary the centroid of the stress. So we've got a triangular distribution. We know that the centroid of a triangle is at the 2/3, 1/3 mark. So this portion of the area of the triangle and this portion of the area of the triangle are equivalent. So we have a centroid over here. So look, we have a moment. The centroid of the object is right in the middle, so that's pretty easy. We've got the centroid of our stress. So we've got some eccentricity. We've got a force P causing a moment on this object, where M is the force times the eccentricity. Again, always remembering that B is there, that dimension B. Now here we have one where the centroid is offset and the stress is offset. So now we've got a very large E. We have the neutral axis is through this line here. We have the centroid of our stress is over here. And so our eccentricity is this total distance. Again, this is all stuff that we've talked about previously, and this is mostly just to be a refresher because I'm going to go through a series of calculations that it's very handy if you remember this for when I do the calculation. It'll be one little check in your mind as you see me go through these steps of the calculations. The calculations that you're not going to be required to replicate, but I think it's very important that you have it in your brain where it comes from. In fact, I'm actually mandated to make sure you have it in your brain where it comes from. Okay. So we have a bunch of different stress profiles here. This one's pretty easy. Its centroid is going to be right through here. This one looks pretty easy. It looks like it's got a mirror line there, so it's going to be right there. This one too, it's not perfectly drawn, but if I was going to eyeball it, I'd say its centroid would be somewhere right around there. This one, no problem. Its centroid is in the center of this stress profile, but here's our object. So the object centroid is here somewhere, and our stress profile centroid is right here. Same with this one, and same with this one. That was weird that the centroids came. Oh no, I see what I did. And then the centroids come in here. So all three of these are equivalent, and all three of these are equivalent. So that means we can approximate any distribution of stress across a system with an axial force and a moment that produce the same effect on the system. So if we know the stress distribution on this object, we can use an analogous point load to represent the force, and we know then we can determine what its eccentricity is because we can determine that based on the shape of this, where the centroid of the stress profile is. And then we can take that force with its eccentricity and rewrite it as a force through the centroid and a moment about the centroid, meaning that this stress profile, acknowledging that there is a dimension B into the page, is the same thing as this moment about the centroid and force through the centroid, all still incorporating that dimension B into the page. All right. That was all the refresher I wanted to go through. Now we're going to talk about the Euler-Bernoulli beam theory. So this is really cool. So we have a bunch of really smart geniuses back in the day. It's a bunch of men because they got all the publicity. A lot of their wives, daughters, and family were also equally smart, but they didn't get any of the street cred. But we'll acknowledge that they were participating in this. So this is sometimes called the engineer's beam theory or the classic beam theory. Now, before this, both Da Vinci and Galileo tried to create a unified beam theory, but they didn't have calculus because it hadn't been created yet, and they didn't have Hooke's law. Hooke's law or Hooke's law? How do you pronounce it? Hooke. Which is essentially about springs. So if anyone's ever studied springs, we give them stiffness ratios, essentially. And so Hooke's law hadn't been created yet, and calculus wasn't, there was a couple people that had just started to dabble in it, but it wasn't really widely understood. So the Bernoulli family, crazy smart people in all kinds of different veins, they had their hands in oh my god.
Hydraulics.
Fluid dynamics. I was thinking fluid dynamics and hydraulics. Euler also big in, I used to have all of this memorized. It's been a day. Feel free to Google these people. You can look them up, mostly just because their families are pretty crazy interesting as well. So it was based on ideas from Jacob Bernoulli. It was finally kind of solidified in 1750 by Euler and Daniel Bernoulli, who was a nephew of Jacob Bernoulli. But everyone was like, okay, that's great, you guys. You've got this fancy beam theory, but no one's going to trust math. Don't be silly. Why would we ever use math in engineering? That would be insane. So no one used it for a really long time. And then around the 1890s, two very different engineers took it upon themselves to prove that this theory could be used to make engineering better. So Eiffel designed the Eiffel Tower and Ferris designed the Ferris wheel using this beam theory. So what we're going to do now is learn the steps of the beam theory, or the principles behind the beam theory, and then I'm going to show you a derivation using that principle, making use of all of those things we just refreshed ourselves on. As simple as, where's the centroid of the object, where's the centroid of the stress profile, and that force with an eccentricity from a centroid can equal a moment and a force through the centroid. So those are all the things we're going to need to know, adding in these next three basic concepts that are part of the Euler-Bernoulli beam theory. So here's the first one. Plane sections remain plane. I've got my handy creepy foam block here. It's unfortunate that we have a fisheye lens because it makes everything look like it's warped when it's not. But you see I've got this pink line down the middle. We're going to call this the neutral axis. And then I've got a series of lines drawn 90 degrees to the pink line. And you can see I've got a little 90-degree mark drawn there. Now, we've previously looked at the fact that when we bend this, at the top, those little squares get smaller, and at the bottom, those little squares stretch out. So, we're getting a change in length up here, where it's compressed, and a change in length here, where it stretches. But, right at that center line there, look at that it's hard. It's hard to do this and hold it and keep it square to the camera. And I'm a mirror image of myself. This line, oh my god, sorry guys. This line here stays completely perpendicular. Or it stays at a 90-degree angle to this line right here. So a plane section will remain plane. A single plane remains at 90 degrees to our axes. So any single plane stays at a 90-degree mark to this neutral axis. To remain plane, we know that the top is squishing and the bottom is stretching, which means we know if we have a change in length, whether positive or negative, we're talking about strain. Well, if that's remaining plane, the top and the bottom must both be squashing and stretching an equivalent amount. Or the strain must be varying linearly with the distance from the neutral axis. There is no change in length at the neutral axis, and there is the equal amount at the top and the equal amount at the bottom, but just in opposite directions. So let's take a look at that. We have, so this is bending, but I've just drawn the neutral axis straight here to make it a little bit easier to talk about. So here's our plane, and this is our neutral axis. And we're talking about it bent here, but we're really focusing on the strain. So it's deformed this amount, and it's deformed this amount. And this are equal. This strain is varying linearly. And what's the relationship between stress and strain? Stress and strain also have a linear relationship. So in normal ranges of materials, we know stress and strain are proportional. That means have a linear relationship using that modulus of elasticity. Therefore, if the strain is linear, the stress must also be varying linearly with its distance from the neutral axes. So that's saying that this stress line is linear, or the stress at this extreme point here and this extreme point here, at this point and this point, are the same because they're the same distance from the neutral axes. One is just compression and one is tension, but the stress value is the same. So what does that give us? Now this is just drawn, this is still this, but rather than waste the space of having it drawn over here, I've just drawn it right here. And you'll see this drawing a lot, people do it a lot. If we have a rectangle in bending, just as it starts to yield at the extreme fibers, we have a stress profile that looks like this. Or what I'm saying is, if this point right here and this point right here are the maximum elastic stress we can see, so if it's a brittle material, that's the ultimate stress, and if it's a plastic material, it's the yield stress. So that point right there, just where we're about to fail this thing or switch into plastic behavior, we have a stress profile that looks like this. Okay, this is where I'm going to go through and do the calculation for you. So knowing what our stress profile will look like just when we hit the limit of the capability of our material. So the yield stress if it's a plastic material, or the ultimate stress if it's a brittle material. We want to figure out what we can do with that information. So let's label this derivation elastic bending. So this means we're talking about anything with an elastic zone. So that's basically all the materials. Everything we're going to talk about has an elastic zone here. We know that we're talking about a member. With a cross section that looks like this. We don't know what it is. We've got two neutral axes normally in most things, and we're going to call this dimension D, and we're going to call this dimension B. So this is the cross section of a rectangular beam, and what we want to look at is what's happening to this beam here. We've got our simply supported beam here, and are you going to mumble while I do this? And this is our D here. I've drawn it as a singular line, but we've got our depth D there. And we're essentially, this is essentially a cross-section of this beam. So we're cutting that beam, and this is what we're looking at. So now what we want to do is maybe start talking about this beam somewhere along its length. So let's say that we hit our yield point at the top and bottom fibers. So top and bottom fiber. What we're really saying is the top of the beam and the bottom of the beam at yield point. Or really, top and bottom just at max stress. and I'm saying the reason I'm being very specific about yield point is because the max stress isn't the same for something with a plastic zone. So we're talking about the end of the elastic zone, but for some materials, that is the maximum stress completely that it can see. So we are going to take a cut of that beam that we were just looking at. And we know it continues here, and we know it continues here, but we're cutting along a plane. So we've cut along this plane here, and there's the neutral axes. And we know that we're talking about this just as the internal stresses hit their maximum at the top and bottom fibers. So here and here. If you guys remember, this was the same thing as it being drawn on a diagonal, but we just shifted this side over, so it was a little bit easier to look at. And remember that this was the entire depth D, so we could rewrite this as saying that that's 1/2 D, and that's 1/2 D. Well, drawing this as a stress can be a bit of a pain, so let's draw it instead. I'm going to draw this a little bit shorter this time. Let's draw it as the force through its centroid. We know that this is a triangle, so the analogous point load for this triangle is going to be 2/3 up along here. And the analogous point load for this triangle, pointing in that direction, is going to be 2/3 down from here. Or we could say P due to compression and P due to tension. Let's just write this here for ourselves. And each of these has an eccentricity. That's the eccentricity for compression, and that's the eccentricity for tension. Well, we have two forces with an eccentricity. We know that we can rewrite that as equivalent moments. Or we can say that we have our P tension and our P compression. If this is our neutral axis or our centroid, this is trying to spin it in that direction, and this is also trying to spin it in that direction. They're both trying to spin it in the same direction. So that's the moment due to compression, and that's the moment due to tension. So look, the PT and the PC cancel each other out, so there's no net axial force on this. They're going to cancel each other out. Some of it's happening at the top, and some of it's happening at the bottom, but they cancel each other out, and the beam isn't moving in space. But we do have internal moments happening here. Now, if you guys remember, each one of these stress profiles really had a dimension B in the background. So like I said, I am really bad at drawing things in 3D, but maybe I can get away with a triangular stress block. So that's our triangular stress block. That is that right there. Remember, this right here was 1/2 D. So that's 1/2 D. And this distance here is B. And this right here was our stress maximum, or whatever our stress is. We can just keep writing stress. What we have is we want to figure out what PC is and what PT is. So what we're saying is that this PC happened in the centroid of this, but it also happened in the centroid of its width as well, or the halfway point. We want to know, essentially, the total volume
of this triangle. So PC equals 1/2 D times B, so the width into the page, times the other leg of the triangle, or our stress. But because it's a triangle, it's divided by 2. It's not a whole rectangle here, it's a triangular distribution. Or we could say that that's the same thing as stress BD over 4. And where it takes place is right there. This was 1/2 D, and this is taking place at 1/3 of that dimension, and this is taking place at 2/3. So remember, the triangular point load is at the 1/3, 2/3 point right here. And we want to know what this distance right here is, EC. It's 2/3 of 1/2 D. So EC equals 2/3 of 1/2 D. Or we have 2/6 D, which is 1/3 D. So we know what our force is, we know what our eccentricity of our force is, and we know that moment equals force times eccentricity. So we could calculate our moment now. Let's go about this the way we used to, where we summed all of our forces in each direction. Let's sum our forces in the x direction, with that way being positive, and we want to know what it takes for this thing not to move. Remember, our beam isn't flying around in space. There's deformation, but it's not moving in space. We have PT going in that direction, which is positive, minus PC going in that direction, which is 0. We have PC and BD are going to be the exact same value, or stress BD squared divided by 4 minus stress BD divided by 4, stress BD divided by 4 equals 0, or 0 equals 0. We have no net internal axial force. Let's sum our moments about our centroid right here, about the z-axis. We have MC spinning in the positive direction and MT spinning in the positive direction. And we want to know what the moment is to keep this in equilibrium. So we have MC plus MT. Well, we want to know exactly what it takes to keep this in equilibrium. So M for equilibrium. We know it's going to have to equal something to stay in equilibrium. So we want to figure out what moment that moment is. So we have M equals PC times EC plus PT times ET. I know, it sounds a little weird, but we've calculated all these things. We know what PC is, we know that PT is the exact same value, we know what EC is, and we know that ET is the exact same value, because we can see it right here. We can literally see it right here in this diagram. So we have PC, which was stress BD divided by 4 times EC, or 1/3 D, plus PT, stress BD divided by 4, times ET, or 1/3 D. So we have a bit of a messy equation right there. Let's take it down and do it step by step. So we have stress B, there's 2 D's squared, so that means D squared, and 4 times 3 is 12. Or stress BD squared divided by 12. Same thing here, so stress BD squared divided by 12. We add these up. We have 2 divided by 12, stress BD squared, or stress BD squared divided by 6. So to be in equilibrium, moment must equal stress BD squared divided by 6. We need this to be true to maintain equilibrium. So we can figure out what our moment is. If we know what B is, and we know what D is, and we know what the maximum stress is, we know what the maximum moment would be for this to remain in equilibrium. This is messy, this little thing over here. Let's put a circle around that and say, all right, everything about this we derived based on the shape of this object. Let's just take that and circle it and say that this is a shape property. So let's call this a shape property. It's shape dependent. In fact, maybe let's give it a name. Let's call it S. So what we're saying is, so let's use S as a placeholder right there. What we've derived is that, that pen wasn't very good. What we've derived is that M equals stress times S. The stress is about the material. This is about the shape. So it doesn't seem like we have much there yet, but for elastic bending, if we know what the maximum stress an object can see is, and we know what the shape of the object is, we can determine what the maximum moment an object can see is. Now, if you guys remember last term, we were able to figure out what the actual moment on an object was. So if we know what the actual moment is, and we can figure out what the maximum moment can be on that particular shape, well then we should be able to say if that particular shape's maximum moment is greater than the moment that's applied to it. If that's true, then our member should work. Now we should factor up our moment and our applied moment, and we should reduce the capacity of our material. But if we do that, we now have the ability to say that our member could work for moment. Sorry. Oh, look at that. We're in the wrong spot. Let me just zip this forward a little bit. Quite a bit off. Okay. So here's what we've just derived. Here it is again. So based on the Euler-Bernoulli theory, just as our steel starts to yield at the extreme fibers, so just as we hit the maximum stress that's in our elastic zone, so just as this is starting to bend like this, when this is hitting the part where it's going to yield, which means permanent deformation, and just as this spot right here is hitting its maximum elastic stress, or there would be permanent deformation, we know that we can calculate what the maximum moment could be. So for the elastic bending of a rectangle, stress equals BD squared divided by 6. But BD squared divided by 6 was all about the shape of the object. We happened to be using a rectangle. So if we just say that that shape property exists for any shape, we can give it a placeholder S. We're going to call that section modulus. That seems like a nice name for it, section modulus. So that we have an equation for any shape. M equals stress times S, or our section modulus for our shape. So elastic bending of any shape where S is dependent on the profile, we can figure out what that maximum moment is. So let's do an example here. Wait a second. Sorry. So if we have if the stress capacity in a 450 deep by 200 wide beam is 20 MPa, so they've said that if the extreme fibers go above this, what is the maximum moment as the extreme fibers reach their elastic limit? So if we go past 20 MPa at the top or the bottom of that beam, we've failed the beam. So we want to know what maximum moment we can get out of this. So if we hit 20 MPa at the top or the bottom, we've failed this member. So what is the maximum moment? They've given us stress equals 20 MPa. And we know that B equals 200 millimeters and D equals 450 millimeters. We know that moment equals stress times the shape property. Well, we know our stress, or our maximum stress, is 20 MPa. And we know that S for a rectangle, and they said that it was a rectangle, is BD squared divided by 6. So M for this particular member is 20 MPa times 200 millimeters times 450 millimeters squared divided by 6. Let's bring out our trusty calculator. We have 20 times 200 times 450 squared divided by 6. Whew, that's a big number. We have 135 times 10 to the 6. We were using MPa, which means Newton millimeters. So this is in Newton millimeters. So this was newtons per millimeter squared. These are millimeters. These are millimeters. So newtons per millimeter squared times millimeter times millimeter times a millimeter again gives us Newton millimeters. Well, once we're talking about moment, we don't like talking about it in Newton millimeters anymore. We like talking about it in kilonewton meters. So we want to get newtons, we divide by 1,000. We want to get meters so we want kilonewtons instead of newtons. We're going to divide by 1,000, and we want meters instead of millimeters. We're going to divide by 1,000 again. 135 kilonewton meters. So this particular rectangle of this particular material, if those extreme fibers start to bend too much or stretch and compress too much, and they see a stress of 20 MPa, we will be able to achieve 135 kilonewton meters in that beam. If we go over that, if we go over 135 kilonewton meters, our beam fails. We can go anywhere underneath that and it works. Just remember, this was the maximum stress they told us we could reach. So we could have 100 kilonewtons and our beam would be fine. If we unloaded it, it would go back to its original shape. But if we go over 20 MPa or over 135 kilonewton meters, our beam will not go back to its original shape if we unload it. It will have yielded. Or worse, if it was a brittle material, it will have failed. So this upper limit is very, very, very important. So let's just go through a thought exercise here. This is going to make it too bright if I turn on my... Let's go through a thought exercise here. We know that if this is our cross section here, we know that this stress profile this is what the stress profile looks like, and it varies linearly right up until this maximum point here. Up to the maximum or yield. If it's a brittle material, once we hit that maximum point there, it fails. If it is a ductile material, we would start to get large deformations at the top and bottom, but look, we wouldn't have reached our maximum stress in here. So what if we went just a little bit past this? So let's draw the same thing again. We went just a little bit past that point. Maybe we get a stress profile that looks like this. And maybe we go just a little bit beyond that. We bend it just a little bit more. We know we're pushing our luck here a little bit because pretty soon the whole thing is going to start to see large scale deformation. What if we did it a little bit more? What if we came down to just a hair shy of the neutral axes, about to see that maximum stress profile? So that all of this side is hitting the maximum and all in compression, and all of this side is hitting it in tension. So we're not yielding it all the way through, we're yielding it just to the neutral axes. We're almost getting to the point, we're gonna have some permanent deformation when we unload it at the top and bottom of this member. And here we're gonna have some permanent deformation all the way down to just shy of the neutral axes. After this, we're going to see large-scale deformations through the whole thing. You almost can think of it as a runaway cart at that point. But right here, we are just shy of it happening. So what happens if we did let our material do that? What if we let it go into the plastic zone? Dun, dun, dun. The plastic zone. So if we let a material with a plastic zone, if it doesn't have a plastic zone, this doesn't work. It will have failed by this point. So this only works in ductile materials. Brittle materials fail after the elastic zone limit is reached. But if we had a ductile material, and we said, okay, how about we let it yield just a tiny little bit? We know there's still a little bit that's elastic, and we'll take that all the way down just to the neutral axes. Let's do the same thing we did for the derivation of our elastic bending, but let's let it go into the plastic zone. So we've got the same section, which has a B dimension and a D dimension. So we've got the same shape. All of this remains the same. We've got that shape and that cross section. But now we're going to let it yield just down to the neutral axis. So this is plastic bending. And just to neutral axes its yield point. So we're going to let that maximum stress get all the way down to just at the neutral axes. So here's our cross section. And now we've got internal stresses where this is compression and this is the maximum stress. And this is tension, and that's our maximum stress. We know as well still that that's half of D, and that's half of D. We can redraw this because we know that we can find the centroids or the analogous point loads for both of these stress profiles. We can redraw this so that that is PC and that is PT. And that's EC, and that's ET, and we know that that is similar to having PT here, and PC here, and MC and MT. So this is the equivalent to this. We've just taken the stress profile, redrawn it as analogous point loads and its eccentricity, and then we know we know that a point load with an eccentricity can be redrawn as a moment and a point load through the centroid, or in our case along the line of the neutral axes. So we've just drawn the same thing 3 different ways. Let's take a look at this stress profile drawn as a very poorly drawn 3D figure. So let's take the compression one. We know that this is the max stress. That dimension is the max stress. This dimension is 1/2 D, and that dimension is B. So the total analogous point load here is our stress times our height times our length, or PC equals 1/2 D times B times stress. It's the total rectangle, so that's it. We've solved for that. Or we could say stress BD divided by 2. Our eccentricity is halfway up it, or EC. This was half of D, and so this is 1/2 of half of D. So 1/2 of 1/2 D equals D divided by 4. Our total moment is MC plus MT. Our PT and our PC cancel out, and we have both things trying to spin this in the same direction. We know that MC equals PC times EC, and we know that MT equals PT times ET, and the values are going to be the same. We could redraw this same thing and get the exact same values. So this is the same as PC EC plus PT ET, or stress BD divided by 2 times d divided by 4 plus stress BD divided by 2 times d divided by 4, or stress BD squared divided by 8 plus stress BD squared divided by 8 equals 2/8 stress BD squared, or stress BD squared divided by 4. So moment equals stress BD squared divided by 4 if we let an elastic or if we let a plastic or a ductile material yield all the way down to the neutral axes. M equals stress times BD squared divided by 4. That is shape dependent. Let's call this one Z. So instead of S, we're going to call it the plastic section modulus Z. Why not P? Well, how annoying would it be to throw another P into the mix? So let's call this Z. So we've got a new shape property. We now know that if we let something yield down to the neutral axes, M equals stress times Z, and Z is simply a shape property. So we have that. That is all calculated out here for you again if you want to go through it and do it yourself. Again, you don't have to memorize this. You're not going to have to do this in an exam in any way. But the reason it's important is that I wanted you to see where these shape properties come from. So for plastic bending of a rectangle, BD squared divided by 4 was all about the shape, and we're going to use the placeholder Z, or the plastic section modulus, so that we have an equation for any shape. That means we don't have to stop and say it is a rectangle. We could go possibly calculate it for any shape and then put it back into the equation. So M equals stress times the plastic section modulus for the plastic bending of any shape where Z is dependent on the profile. Now, if any of you are British, the elastic modulus is called Z and the plastic modulus is called S, just to completely screw with all of you. Now, we're going to stick to our methods here, but just be aware that sometimes these terminologies can change depending on where you are. So let's do that same problem that we had done before. So let's look at this same rectangle. So we now know this was elastic. They've now told us that it's a yielding material, and we want to do the plastic. We want to let this go, plastic. We want to let this go just to its plastic limit. So our stress stays the same, our maximum stress stays the same, our B stays the same, and our D stays the same. The only thing that's different here is that they have told us we can use our plastic section modulus. We are going to let this yield down to here. This example, we said only the extreme fibers could hit that maximum or yield stress. Here, we're going to let it come all the way down to the neutral axis. There'll be a little bit of permanent deformation, but we're going to live with it. And let's see what happens if we live with that little bit of permanent deformation. M equals stress times Z now. Z equals BD squared divided by 4. So our maximum moment in this example is 20 times 200 times 450 squared divided by 4. Let's plug this into our calculator. 20 times 200 times 450 squared divided by 4. We get 202.5 times 10 to the 6 Newton millimeters. Let's convert that to kilonewtons. 202.5 kilonewton meters, convert it to kilonewton meters. So if we have a plastic material, in some situations we might let it yield just to the neutral axes. And look, we get a higher moment capacity. But remember, if this was a material that did not have a plastic zone, we would fail our material if we tried to do this. So you have to know about what type of material it is before you can make a choice like this. So here's that calculated out.
So if we know Euler-Bernoulli theory can help us calculate our moment equations for both plastic and elastic materials, and we know that we kind of go through that process. I've used a rectangle as an example, but we figured out that there's some element within that is all about its shape. And so if we are always talking about that section as a placeholder that has to do with its shape, it can simplify our calculations. So we know that we have this shape property that we can leave as a placeholder and talk about these things as an unknown shape that we haven't defined yet. And we can use that as the placeholder for us. But there are a few other things that we can do using the Euler-Bernoulli beam theory. Now, this is not something that you would have to calculate. This would be well beyond the course. But you remember how we talked about last week that shear stress and strain have a very similar parallel to axial stress and strain. So if that's our strain, we have an angular strain here, which we talked about very briefly last week. It was not something you had to memorize, has a relationship to shear strain. So if we know some things about shear strain, and this is not something you need to know, we can go through a similar process that we just did for elastic and plastic bending and look at, and we can end up deriving another shape property. So again, this is just a shape property, I. Now, to really mess with your heads, I is called moment of inertia. So lock that down in your head. In fact, I'm probably even going to add it to the slide. Moment of inertia, I thought I had that in here, is a capital I. Capital I is a real pain in the butt for inputting in anything because most fonts show a capital I as being a straight line, so it looks like an L, so I always have to remember to either find a font that makes it a capital I or use the Greek symbol for it because it's the only way I can get a capital I to show up. But this is another placeholder for shape. Now, this can be derived for almost any, well, it can be derived for any shape, but that is not something we're going to do in this course. We've had to do it a bunch, lots and lots of times, derive I. I remember learning how to do that and thinking it was just the coolest, most elegant thing in the world. I spent a lot of time alone. So, knowing that, if this is our placeholder for shape I, and this is the bending or the angular strain equation. Angular strain, again, you do not have to do that. We can integrate and we can find rotation at any point along the object that's in bending. We can integrate again, and then we can find the actual amount the object has deflected based on that angular strain. So if we have a beam that's bending, you can see that there's an angle there, and that is part of this process. But we can go through that process and look at this. Now this is for a simply supported beam. We have other scenarios that are not a simply supported beam. Simply supported beam. The deflection for a simply supported beam is 5WL. W is our load, our serviceability load, because we're talking about deflection, times our length to the power of 4, divided by 384 E, which is our modulus of elasticity, and I is our shape property for our object. So similar to our moment calculations that we've done in the past, we know, in fact, we did this last term, we figured out the serviceability W. So for moment and shear, we were using WF, but remember I told you to always calculate W as well, or the serviceability, so W for dead and snow, or W for dead and live, and then W for live and W for snow as well. I told you to track those. Well, W, we know. L, we would know because of its length. E, we would know because of the material properties. So the only things unknown are deflection and I. If I is tied to its shape, we should be able to determine what the actual deflection of a member is. Remember last term we already figured out what the allowable deflections are, so now we should be able to compare those things. So the big takeaway here, deformation and strength are related for each material, and we have data on most materials available to us when they're in a normal range of behavior. So remember that elastic zone, and just if it's a yielding material, we can go just up until it yields up to the neutral axes. That's the most we'd ever let anything go. And there are section properties that allow us to calculate the strength and deformation shapes. So our section property S, Z, and I. And actually, for axial forces, we used area a lot. So that's 4 different shape properties: area, S, Z, and I, which are just properties that have to do with the shape. We can combine our knowledge of the shape and the material, and then we can design members to a certain strength and a certain deformation. You are not going to have to manually do the derivation for S and Z for other shapes, and you didn't even have to do it for I for a rectangle. But the only shape we've looked at today is a rectangle, a solid rectangle. We know, so that's kind of good for wood. Wood is often in a simple rectangle. But our steel isn't usually in a rectangle. We often have either a hollow tube or an I section or a W section. So we know that there's a process. We know we can figure out A. We know we just derived I, or I showed you a very crude approximation of it, and we manually derived S and Z for a rectangle. Well, I'm never going to make you derive those again. From this point on, you can look up how to calculate the section properties. So for this I-beam, and don't worry, I'm going to make it even easier, so don't worry too much. Here is the area for the I-beam. Here is I, or the moment of inertia, for the I-beam. Here is S, or our plastic section modulus, for the I-beam. And here is Z, or the plastic section modulus for our I-beam. R, right here, don't worry about it too much. We're going to use it a little bit later in the course, but it's not something we're really going to talk about. It would happen to be on this page, so I just don't even worry about it right now. So here's a whole bunch more shapes. This is uploaded to Quercus, so you can calculate A, S, Z, and I for any shape you want. But
For the members that we already know, why would we waste our time doing it when we know it's a section that exists in the world with actual hard dimensions, so a depth and a width, not just a triangle? They have already done this for all of the steel sections. So that makes our lives one step easier, that for a steel section, we can just go to the page that has that steel section in it. We can look up A, we can look up S, we can look up Z if we're going to let it yield all the way to the neutral axes, and we can look up I when we need to talk about deflection. Oh, I didn't circle them. So here is area, here is I, here is S, and here is Z. We also have R, J, and CW. We're going to use those when we talk about steel, but they're way beyond anything you need to know about. But look at this. We have XX and YY. And look at our little diagram here. They've given us two neutral axes. These are saying what neutral axes we're bending about. So if we're talking about axes XX, so that's this zone right here, or our XX axes, that's saying we're bending about this axis. So we're bending it like this. So this is the axis that comes around and cuts through it like this. So we're bending it like this. The YY axis right here is saying that we're bending it like this. So XX is our strong axis and YY is our weak axis. That's going to be important when we talk about buckling in a couple weeks as well.
I'm going to just have a little joyful departure for fun. Share something with your students.
Okay.
See if it works. Deriving the chain hang shapes for the radial cables.
He's very excited. He's very excited about this.
Never done this before.
You want me to hold it for you?
Let me just see here. Oops. Set it up here.
They have something that's built in the world that they can't determine exactly where all the parts are, all the points are on it.
Well, this is not good. I'm not going to be able to share this effectively, am I?
I don't know. I don't know what
hard,
you're doing.
It's hard to see, and I can't press go.
So they have something that's built in the world, and the only thing, and they know a few things about it, and they know how long each member is. So they know where it is here, and they know where it is here, and they know how long each member is, so they need to figure out exactly where each node is along it. And so he's been trying to formulate a way to determine that. It's all he's going to want to talk about tonight. All right, so let's do a few examples now. All right, let's look at a practical example. So we have a simply supported beam that spans 4 meters. There's a factored load on the beam of 7.8 kilonewtons per meter. So we have a uniformly distributed line load. And the reduced capacity of the steel is 0.9 times 300 MPa. So they've given us a factored load, so that means that our 7.8 kilonewtons per meter is a W with a little f. We don't know much about reduction capacity and things like that, but they're telling us that our reduced capacity is 0.9 times 300 MPa. So we're going to take them at their word for that. But that means whatever we're calculating, we get to use that little r to say it's a reduced capacity. What depth does it need to be if it's a 13 millimeter wide rectangle? Check for elastic and plastic behavior. So I always like to start with what I know, because this is a word problem. The final question in the exam threw off a few people simply because I added words into it. What you need to be able to do is stop and distill it down and pull out the things that are important. So, what we know, or what is given. We know that the length equals 4 meters. They gave us WF. They told us that the line load is 7.8 kilonewtons per meter. They gave us the reduced stress. They said it was 0.9 times 300 MPa. So that is the reduced capacity of the steel. If we multiply this out, the reduced capacity, that's saying we will not let the steel see more than that. If we go over that stress, we say that that steel has failed. It doesn't work anymore. It's ruined. So this is, if we multiply, let's multiply 0.9 times 300, we have 270 MPa. They've given us that B equals 13 millimeters. They've asked us to calculate what depth beam we need for D elastic and D plastic. So let's start with the elastic one. Sorry, I'm used to writing all in capitals, but because I'm doing stuff with my children lately, I've started writing some things in lowercase, and it's really throwing me off when I'm writing lately. Okay, elastic. We know that the elastic moment equation is M equals stress times section modulus. They've told us that it's a rectangle. So S equals BD squared divided by 6. Remember, this was only for a rectangle. A different section, we would need to look it up or calculate it. But we don't know what M is. We still want to know what M is. Let's take a look. We know that we also have a simply supported beam with a uniformly distributed line load on it that they've told us is WF equals 7.8 kilonewtons per meter. Oh, we also know that this is 4 meters. Now, last term, you had to do this by method of sections. We're pros at that now. We're beyond that. We know that calculating the maximum moment that this sees due to this load is our equation MF equals WF L squared divided by 8. Well, we have WF, we have L. We can solve what the maximum moment is. So MF equals 7.8 times 4 squared divided by 8. 7.8 times 4 squared divided by 8 equals 15.6 kilonewton meters. So we have the actual moment that this beam is going to see. We know that MR is going to equal our stress R times our S, or BD squared divided by 6. The thing we don't know here is D, or what we want to figure out is D. That's the thing that's important to us to determine. So MR equals stress R BD squared divided by 6. Let's rearrange this to find D. You don't have to, you could plug things in and work it out. Depends how you like to write things. I switch, I'm going to rearrange this to solve for D. So we're going to have 6 times mr divided by stress divided by B, all square rooted. So D equals, now here's the thing, we want mr to be greater than mf. What if we said that the perfect design would be just as mr equaled mf? That's perfection. If we had something lower than that, we know mr would work. If we had something greater than that, we know mr wouldn't work. So having mr equal mf is the exact perfect design. Let's see if we said mr equals mf, what D would be required. So 6 times 15.6. Now here's the thing. This is in kilonewton meters. We like to talk about things once we're using stress in Newton millimeters. Remember in those last examples, we got things in Newton millimeters because we were using stress. We're going to want to use this as Newton millimeters. So times 10 to the 6, because we're going to multiply it by 1,000 and then multiply it by 1,000 again. Divided by our stress, 270 MPa, divided by our B, which was 13 millimeters. We can plug all of that into our calculator. So we've got the square root of 6 times 15.6 to the exponent 6 divided by 270 divided by 13. We get 163.3 millimeters. So for elastic bending, we need a beam that is at least 163.3 millimeters deep. If we have one that is deeper, our MR would go up. That is wonderful. We would have an MR greater than MF. If we used a beam that was shallower, so say we used one that was 160 millimeters deep, our MR would be a lower value, which means then our MR would be less than MF. And if MR, our reduced capacity, is less than our factored moment, we are going to have a failure. So for this to work, if it's elastic, we need a beam that is at least 163.3 millimeters deep. Let's do it if it's a plastic material, and they've allowed us to go into the plastic zone a little bit. So now M equals stress times Z. We know that Z for a rectangle is BD squared divided by 4. So we know that M equals stress times BD squared divided by 4. Let's rearrange this, and we get that D equals the square root of 4 MR stress R B. So it's the same equation. The only thing that's different is that 4 and that 6. Our MF stays the same. That's something that was applied to it. So if we want to know what will make this work, we want to say that our MR is at least 15.6 kilonewton meters. So if we say that MR is at least that, we will have a section that works. Or D equals the square root of 4 times 15.6 times 10 to the 6, because I've converted that kilonewton meters into Newton millimeters, divided by our reduced stress capacity, or 270 MPa, times B, which is 13. We can plug this into our calculator, or square root 4 times 15.6 exponent 6 divided by 270, divided by 270 divided by 13, and bracket, we get 133.3 millimeters if plastic. So if we said that we allowed this to have some small amount of permanent deformation, we allow it to yield just down to the neutral axes, we can use a shallower beam. So we have to know when we can use plastic and when we can't. Well, first off, if it's a brittle material, we can never, ever, ever use plastic. It would fail. There is no plastic zone. This is the only thing that would work, because when we hit the end of that linear elastic zone in our stress-strain diagram, our material fails. If we have a material that is ductile or has a plastic zone, we will sometimes allow the material to yield down to the neutral axes. As we go forward, I will show you when and where when we do that with steel beams in a couple weeks. So here is that problem worked out. Let's do one more example. So for this one, they've said, what is the stress on a simply supported W310 by 39 beam that spans 5.6 meters and has a factored load of 27.5 kilonewtons per meter if the beam remains in the elastic zone. So, given, what are our things that we know here? Let's make this bigger and make sure I'm writing where you guys can see. All right, so, given. We know that we're talking about a W310 by 39. We know the length of our beam is 5.6 meters long. That's the same thing. We might need that, maybe we don't. Sometimes it's good to get in the habit. We know that WF equals 27.5 kilonewtons per meter. They've told us it's elastic, so M equals stress S. So we need to know what M is, we need to know what stress is, and we need to know what S is. It's all kinds of things we don't know still here. Well, S, we know, is dependent on shape. Do we know what our shape is? We know that we have a W310 by 39 beam. So maybe we could go look that up. And I just realized I probably, if I was smarter, I would have pre-lined that up. Let me get that open up for us. That's not the right course. You did that one already. Structures 2. I'm just opening a file here, people. And Dave is muttering in the background, which certainly isn't helping my concentration. We could go to section. We could go to section properties here, but then we'd still have to calculate a specific I-beam. What if we went right to where is it? Are we missing one here? Okay, so that should be called steel section properties. I will make sure that I have the right things uploaded for you. Steel shape properties and all shape properties. So I'm just going to make sure those files are uploaded correctly for you guys. They might be uploaded properly for you. So here we are. We have our all of our steel sections. And let's find where, what the, okay, so this is just all sections. Where are our steel sections? What is happening here? Sorry guys, I am just looking for a very specific file. It's like it got deleted on me. Yeah, some things did get deleted. Okay, steel sections. I will make sure steel sections is uploaded for you guys. So there were section properties for all the different shapes. We could use that. We could look at the one, I'm guessing it's probably one of the first slides. So we could manually calculate this, but people have done this a bunch for us already, and we can go to the actual steel book where they've already calculated this out for many of, you guys can't see anything I'm talking about. Oh, all right. Let's try again. Okay, you have two files uploaded. One is section properties and one is steel sections. The section properties are all the different shape properties that you could calculate these things on your own, including an I-beam. But for some materials, we have even more information, like our steel sections, for example. So here, you guys don't want to know, but verify. So here we have a W310 by 39, and look at this. We've got some section properties. For a W310 by 39, our SX is 549, but look up here, by 10 to the 3 millimeters squared. So that's really important. We have SXX equals 549 times 10 to the 3 millimeters squared. So we have information now about our shape. So we know that it is a simply supported beam. They said it was simply supported. So maybe we could calculate what the M is on this, or the moment on this. We have a beam with reactions and a uniformly distributed line load on it. And they've told us that that WF is 27.5 kilonewtons per meter, and that this is 5.6 meters long. We know that MF equals WF L squared divided by 8, or 27.5 times 5.6 squared divided by 8. We can plug this into our calculator. 27.5 times 5.6 squared divided by 8. We have 107.8 kilonewton meters. We know that that's also equal to 107.8 times 10 to the 6 Newton millimeters, that those are equivalent things. The question asked for the stress. That's what they wanted, is what is this stress under elastic behavior? So we know that M equals stress times the section modulus, or stress equals M divided by S. We know what M is. We know what S is. We can calculate what the stress is. We have 107.8 times 10 to the 6 Newton millimeters. And our SX is 549 times 10 to the 3 millimeters cubed. I'm writing everything wrong today. Millimeters cubed. So we have Newton times millimeters, and then divided by millimeters cubed, we're going to end up with newtons per millimeter squared. And we can calculate this, or why don't I just write the units in here? So this was Newton millimeters, and this is millimeters squared. And we are going to get 107.8 times 10 to the 6 divided by 549 times 10 to the 3. We get 196.4 newtons per millimeter squared. And we know newtons per millimeter squared is stress equals 196.4 MPa. So we figured out what the stress is on that beam. Now, what if I told you that the maximum stress would be that 270 that we did in that last example? Would this beam work? Yeah, seemed like it will, because our stress is less than the maximum stress that we've said this steel could see. Now, I'm not saying that that's always the number that we're going to use. I just wanted to give you something as an example here. So again, that's worked out here for you as well.
So what are the biggest takeaways that we determined here today? I mean, obviously we figured out that S and Z and I are a section property of shapes that we can use for to calculate moment, which is huge. That is and deflection. Those are huge things. But let's stop. What are the biggest things that are going to be helpful to you going forward? We're going to have to do moment calculations, and we're going to do that, and that's mandated, and we're going to go through all of that. But here's the thing that I want you to remember forever and ever and ever going forward. The most important thing about bending for you to remember is that length and depth have the biggest impact on the design. So let's take a look at this. Length, when we're talking about moment, it is W times the length squared divided by 8. Remember, we did that last term. We determined this. We calculated this. We manually came up with this equation. Deflection, we talked about here today. I didn't make you derive it because it had to do with angular strain, integrated to get rotation at a point, integrated to find deflection. But hopefully you trust me at this point that the math shakes out. It's 5W, which is the load. So our load is just a linear thing in these equations. Length is squared, and in this one, length is to the power of 4 divided by 384 EI. Length is squared for strength and to the power of 4 for serviceability. Depth, or our section property, and we're going to use the rectangle just because it's the one we've talked about, that it's the easiest, but these factors are in there the same way. BD squared divided by 6, and I for deflection is BD cubed divided by 12, or D squared for strength and D cubed for serviceability. That means if something doesn't work, shorten the span or deepen the beam. It is going to have a much bigger impact than decreasing the load or making the beam wider. If
you add length to the span or shallow up the beam, you're going to have the biggest negative impact. Trying to make a beam shallower is going to be much more, it's going to be much worse on the design than making it narrow. Or increasing load is not going to be as detrimental as lengthening the span of the beam. So these are really important things for you to remember. Length and depth, super duper important. So deformation and strength are related for each material. And we have data, I think I already showed you this. We have data on most materials when they're in normal range of behaviors. There are section properties that allow us to calculate strength and deformation of shapes. We combine our knowledge of the shape and the material, and then we can design our members to a certain strength and a particular deformation. So the strength, we know what loads we need to support. We know what our deformation limits are. That's the stuff we determined last year. Now, specifically for things in bending, we now know how to determine what its actual capacity is and what its actual deformation is going to be. So going forward, you should know a bit about elastic and plastic behavior, and you should know where and how to calculate properties of a section, and you should know length and depth are the most important things, length and depth are going to have the biggest impact on the structural design. For this course, your takeaway tips, you should remember stress and strain and modulus of elasticity and their equations. You should remember that we sometimes show these things in 2D. Plane sections remain plane. So, strain varies linearly from the neutral axis, which means that stress also varies linearly from the neutral axis. Elastic and plastic stress profiles of a rectangle we looked at. You should at least recognize what those look like. And equations we derived for S, Z, and I of a rectangle. You should know BD cubed divided by 6 and BD squared. BD squared divided by 6 and BD squared divided by 4. And you should know BD cubed divided by 12. You should know how to find, but we could also calculate it, S, Z, and I for any other shape. So those ones I just said are just for a rectangle. We need to know how to look up and find S, Z, and I for any other shape. So you're going to do an assignment where you're going to do some examples looking at these things. And then next week, we're going to start taking this knowledge of axial stress and strain and bending stress and strain and start applying them to our very first material. And the easiest one that I find to work with is steel. So we're going to be starting our steel lectures. All right.